Chapter 7, Think and Solve. How much work is done when you push a crate horizontally with 500 newtons across a 10-meter factory floor? And so the work is, when it asks how much work is done when it's basically asking how much work are you doing when you push it. So if I'm doing this, I'm 100 times 10 or 1,000 newton meters or 1,000 joules of energy is what I'm putting into it. If the force of friction is 70 newtons, show the kinetic energy gain is 300 joules. So the kinetic energy, changing kinetic energy is equal to the total work done. Total work done would be the total force times the displacement. So if I'm pushing with 100 newtons in one direction and friction 70 newtons the other direction, that's a net of 30 newtons in the direction of movement. So 30 newtons times 10 meters gives a 300 joules of energy. So that means I'm putting 1,000 joules into it, and the total work is 300 joules. That means there's a gap. There's a missing 700 joules. I'm putting in 1,000, and I have only 300 to show for it. That 700 is the work being done by friction. It is a loss of the energy of the box because the 70 newtons is opposite the direction of movement. And so you end up with negative 700 joules of work being done by the friction. And where else does it go? Potentially it could go into the sound, depends on if it's scraping, if you hear the scraping or not. But most likely, most of it's going into heat. In essence, the 700 joules of energy is being converted into the temperature of the box on the floor. Number 44. Belly flop Bernie dives from atop a tall flagpole into a swimming pool below. His potential energy at the top is 10,000 joules. What is his kinetic energy when his potential energy is reduced to 1,000 joules? This is straight up conservation of energy. We assume no air resistance. We're not worrying about any loss there. We also assume he starts at rest. So his entire energy initially is 10,000 joules. It's 10,000 potential and 0 kinetic. So as he falls, so we get see if we can get my hands on the screen here. So if this is kinetic down here and potential up here. So as he falls, they are switching positions here, but the total stays the same. So when his potential is 1,000 joules, that means 9,000 joules went somewhere, and it went into kinetic energy. Now, I know energy is conserved here, given the stuff I ignored, because the force acting on him, the reason he's falling is the force due to gravity, which is a conservative force. Energy is conserved. 45. Nellie Newton applies a 5 Newton force to the end of a lever, which has moved a certain distance. The other end of the lever moves 1/3 as far, shows that the force is 150 newtons. It's awkwardly worded, but basically you have a lever here with a fulcrum, and so as you apply a force on one side, there's got to be, basically what can I lift on the other end? And because of conservation of energy, this is sort of ideal, 100% efficiency. She's applying 50 newtons of force, presumably down. Now, we don't know exactly what it is. I'm just going to say 3 meters down. So it applies 50 newtons of force 3 meters down. She does 150 joules of work. That means I can do 150 joules of work on the other end. Again, whatever energy I put into the system can get 150 joules out. And so if it only moves 1/3 as far, then, well, 1/3 times just a second, I lost track there. So 50 newtons of force being pushed 3 meters, doing 150 newtons of work. So the lever on the other end is moving 1/3 as far, so it moves 1 meter. So 1 meter times 150 newtons. And it's basically work in equals work out. This is it shows up more in thermodynamics, but that's basically you put energy into a system. Ideally, that system can now do that amount of energy. So if I put 150 joules of energy into a system, it can do 150 joules out. As we talk about in chapter 18, you'll never actually get all of it out that you put into it. It's impossible. That you'll never break even. So there's always a loss somewhere. So 49, how many watts of power do you expend when you exert a force of 50 newtons that moves a crate 10 meters in time interval of 4 seconds? Now, we've talked about work being done, how much energy you put into the system. So that would be 50 newtons times 8 meters. Again, assuming that the 50 newtons is all in the direction of movement. So that's 400 joules of energy being put in. Now, the part we didn't talk about in class, or may not, it depends on which semester you're watching this, Power deals with the rate at which you're using the energy. So it is just purely the energy put into it divided by the time. So that's 400 joules divided by 4 seconds, or 100 joules per second, which is 100 watts. A watt is just a joule per second. It's the rate at which energy is used, or the rate at which energy is put into a system. And that's it for the Think and Solve from Chapter 7.